And so let's draw a few conclusions for this. So first, a short summary. If you start with the right foundation, and it has, although it's a very simple foundation, you have a mathematical universe, you have operations, your operators. It took me a long time until I actually saw that this is all what's needed, that this is the right conception, that this is the right foundation. And once you have that, then abstraction algebra gives you a simple and elegant formal language with a simple, elegant syntax and semantics, and it provides the proper setting for alpha equivalence. You can define alpha equivalence in a purely semantic way, in a simple way, and it's the same as the usual syntactic definition or characterization of alpha equivalence. So, and on top of this, once you have abstraction algebra, you can derive from this abstraction logic. Again, it's simple, it's elegant, and it unifies proof theory and semantics-based approaches to logic. So abstraction logic itself is, I think, a nice mathematical theory. It has theorems that are easy to state and understand, but they may have long and technical proofs because of the syntactic side that is always involved. And, well, in my opinion, abstraction logic is simpler than first-order logic. We have seen that there are just three constructors to form terms and templates. So certainly simpler than what we have in first-order logic. But on top of that, it also has general binding. So it really combines the best of two worlds. The best of the worlds from first-order logic with the best of type theory without the drawbacks of the two. Okay, so that's a summary, and where do we go from here? So one big issue that isn't fully resolved yet is completeness. I thought I had a proof. Turned out I don't really. But I think the strategy is still valid. And
Helena Rashowa.
So the strategy is to build the Rashowa model, and for deduction logic with equality, for that theory. And I'm calling it like that because really I got the idea of how to make abstraction logic precise. This was inspired by Rashowa's book, an algebraic approach to non-classical logic. And but the construction itself for the Rashowa model is basically what you do when you form the Lindenbaum-Tarski algebra, right? That's very similar. That's why you need some theory here that also has equality, and in this case, deduction logic with equality. Yeah, so I think that's the right strategy. I think that will lead to completeness of deduction logic with equality. But I did this proof a few years ago, and I did it before I had this new version of abstraction logic with a logical order. And so I still need to work out all the details until I'm sure that this all works. And I really would like to do this in Fractal itself. And I think that makes sense because although completeness, it's a theoretical property, really what it means is abstraction useful in practice, right? Can I show everything with it that I would like to show? And this flaw that Zap has found there, actually I would have found myself if I had just implemented this and started working with it, because I would have seen very quickly that certain things I cannot prove, right? I think, well, it's very important to prove completeness, but I think it's just as important to build an actual system, and maybe I do that before I return to completeness. Well, a very important thing is also a very important thing here is also what's the connection of abstraction logic with established topics in logic, right? There are so many things in logic. Of course, propositional logic, intuitionistic logic, intermediate logics, algebraic logics, first order logic, second order logic, intuitionistic higher order logic, dependent types, modal logic, hybrid logic, quantum logics, nominal logic, infinitary logic, homotopy type theory, so many things. But what I'm thinking is, I think all of these special logics are probably just abstraction logics. I think that you can probably represent them all in the framework of abstraction logic. But that's just an intuition I have. You have to do the actual work and try to do this. And that's actually a lot of work if you want to do it properly and in all detail. And also, again, I would like to do this in Practa, where I can make sure that I don't introduce any errors here. And for example, also a very interesting topic is algebraic specification. And in algebraic specification, they have this notion of institutions. And the reason why institutions have been introduced there is, I think, because well, algebraic specification has use for lots of different logics, and these logics don't really fit into a common framework, and that's why institutions are there to provide this common framework. But if we have abstraction logic and all of these logic actually fit into abstraction logic, then we don't need institutions. We can do algebraic specification just on top of abstraction logic. And things like theory interpretation must be implemented then in Practal, of course, as well. And I think that should be also nice to do for abstraction logic, because just like first order logic is just a theory and axioms. Then things like what is the relationship between abstraction logic models, for example, and general models, or Henkin models. Well, what I think is, yes, probably, my intuition there is, if you, for example, go and write higher order logic as a abstraction logic, then the models that you will get for this embedding of higher order logic and abstraction logic will correspond to the general models of the original higher order logic, for example. But, well, you have to work this out in detail and see if this is actually true, if this correspondence is one-to-one, or what's actually going on there. Also interesting is things like Boolean variant models, and these actually inspired the idea to use a logical order for abstraction logic. I saw a paper on forcing by a former PhD student of Thomas Hayes, where he, I think, formalized forcing in Lean, and as part of this also formalized Boolean variant models, I think. And I saw that this should also work. This should also fit very nicely into the abstraction logic framework. And so now, with the concept of logical order, I think Boolean variant models probably also become a special case of abstraction logics. Well, and there are so many more topics in logic, and it would be interesting to view all of them from an abstraction logic point of view. So then there are, for example, there are these topics like rewriting and classic automation, and I think term rewriting for abstraction algebra. I think there should be a good story. I think this should be interesting. We know that higher order pattern matching is undecidable, but I think abstraction algebra pattern matching should be decidable, just like second order pattern matching is decidable. I once had some prototype implementation that seemed to support this, and but you have to look into this in detail, implement it, and then also prove that it's actually decidable. And things in automated theorem proving, like resolution, superposition, sequence calculus, we have seen that sequence calculus arises naturally for abstraction logic, right? So I think these kind of automated theorem proving techniques should also be a natural fit for abstraction logic. But this work needs to be done. What about AI and abstraction logic? I think the two big topics here, auto-formalization and what DeepMind did with alpha proof, I think they actually are very good news for abstraction logic as well. So for auto-formalization, abstraction logic seems like a great target for conversion between logic and natural language. And I once saw a talk about controlled natural language, I think, where they mentioned that they had this problem, what to do with universes, because they don't really have a correspondence in the natural language world. And, well, universes don't appear in abstraction logic. Well, they can appear if you want to, but then you're actually talking about them, and then they're also appearing in the natural language. If you're not talking about them, they don't appear in abstraction logic, right? And I think that's a big advantage, that abstraction logic doesn't have some of the restrictions that types introduce. And I think similarly for neuro-symbolic automation like alpha proof, I think abstraction logic can really unleash the creativity of AI by giving it a truly unrestricted mathematical universe to play with. All right, so the big thing to do, of course, is to actually implement abstraction logic as Practal. I'm using TypeScript for this. That's actually, I think in the beginning it was a little bit unorthodox choice because, well, based on JavaScript and for a theorem proving system, but I think it fits actually very well with abstraction logic because abstraction logic also has no types, but of course you could layer heuristics on it for automated theorem proving, just as TypeScript layers heuristics for types on top of an untyped programming language. And so in 2023 I did a first VS Code plugin that implemented a little bit of syntax and stuff for a former version of abstraction logic. And this is actually where the idea comes from, that templates can be premises as well. Before that, I was focusing on terms, and I didn't really take templates serious as part, of the natural foundation of abstraction logic. But when I was building this plugin, I saw that templates are really important cornerstone, and that inference rules are axioms, are just axioms as well. And now that this is part of abstraction logic, I'm working on a new kernel that based on natural reduction and sequent calculus. And I'm also considering AI and natural language support from the start. I'm considering from the start how do I build Practal so that these things can be integrated nicely. And so I'd like there to be two versions of Practal Desktop that you can just run on your own computer. And but I also want to develop Practal as a cloud platform, and in that sense Practal is an evolution of a previous project I worked on, Proofbeer. Yeah, that's it. Thank you.